base needs just a bit more length to match, and bam, done. Oh, hi. I was just finishing up my PCB layout there. I know, we've talked before about what a board design ninja I am. But you know, today, that just doesn't cut it anymore. Hi, I'm Amelia Dalton, host of Chalk Talk, which you probably already knew. Yeah, being a PCB ninja is so last decade. Today, everything is connected to everything else. You've got your internet of hamster wheels connected to a centralized system of, well, never mind. The point is that PCBs are tightly integrated into systems, and you can't just do your board in isolation. The board depends on the FPGA, and on the connector, and on the interface on the other board, and on the protocol, and you know the deal. It's time to look at the big picture. Today, my guest is Hemant Shah of Cadence Design Systems, and we're going to level up. We're going to look at how Cadence's Allegro and Sigrity help us design products, not just PCBs. Before we get started, don't forget to click that link. There you can download a free tech packet that includes an article, white paper, and customer success stories about this topic. Hi, Hemant. Thank you so much for joining me today.
Great to see you, Amelia.
So you and I have talked a lot about PCB design before, but today we're going to move up a level and look at the whole product, right?
That's right. We're going to look at the end product our customers create, not just the printed circuit board design.
Okay.
So many companies talk about how efficient you want to be with interactive editing. Some people want to talk about how multiple engineers can work concurrently on a schematic. But what we're going to talk about is more than schematic capture, more than the layout. Talk about how multiple boards get into a product, or a board gets into an enclosure, and how you can make it easy for our customers to create that end product.
Okay. So Cadence does a lot of chip and package design in addition to board design. Now, I assume that comes into play here?
It does, but it's more than that.
Okay.
What we're going to look at is how do we make it easy for our customers to make sure that the board they're designing is going to fit into the enclosure.
Okay.
And how do we make sure that that interaction with the mechanical designer is really efficient, and you don't have a whole lot of unnecessary iteration between the mechanical designer and the electronics designer.
So we did a Chalk Talk with Brad Griffin about Sigrity, and I can see how power and signal integrity could play an important role here.
Absolutely. That's an essential piece in designing today's printed circuit boards or the end products that we're talking about, because a lot of these products have advanced standards-based interfaces like DDR4, PCI Express, serial ATA. The list of those standard interfaces goes on and on.
Yeah.
And these interfaces are continuing to use lower supply voltages, going down to 1.8, 1.8 to 1.2, and so on. And these signals are getting very sensitive, as well as require a good power delivery network to make sure it's clean power is supplied to them.
Right.
And so having the signal and power integrity analysis done during the process, or the signal and power integrity analysis driving the entire PCB design flow, is very, very important.
So we're hearing more and more about constraint-driven design these days, and you guys have been doing that for a long time, right? Let's talk a little bit about Cadence's constraint-driven flow.
So Amelia, you're right. We have been doing constraint-driven flow since early 2000s, but it's not a stationary or constant thing. Constraints keep changing as new interfaces come in, as new manufacturing technologies are used by our customers. There has to be new constraints that our system needs to support. For example, when you deal with HDI designs, there's new manufacturing rules come into play, and our constraint-driven flow has to be enhanced to handle those constraints to continue to provide the benefits of a constraint-driven flow that our customers expect: predictable design flow, shorter design flow, and avoid any unnecessary iterations, and avoid finding problems in the lab.
Okay, so Hemant, what does that buy us? So what are the advantages here?
So there's two things there. One is constraint-driven flow has been around since early 2000s, as I said, but we acquired Sigrity technology a couple of years ago for signal and power integrity, that is PowerWare.
Okay, yeah.
And what we've done is over the years, last few years, we've tightly integrated that into the Allegro constraint-driven flow. So now what you have is a solution of Allegro and Sigrity working together. And we have a saying which says Allegro and Sigrity are great alone, but better together.
Okay.
And to answer your question, what do we buy? You have to look at how the constraint-driven flow works.
Okay.
So the way our customers use this constraint-driven flow is they use signal integrity and power integrity analysis upfront to define constraints, embed those constraints in schematics. In the constraint manager, that's the same constraint manager used throughout the design flow. Pass those constraints to the layout. Those constraints are then used to do critical component placement. Then that same set of constraints are used to guide your routing in interactive routing.
Yeah.
And then once you're done with that, then you can do the power-aware signal and power integrity analysis to verify that everything is still accurate before you hand off your design to manufacturing.
Gotcha.
And if you look at the benefits our customers derive, is that they get a shorter, predictable design cycle with Allegro and Sigrity constraint-driven flow. We've had customers that have reported up to 30% improvement in their design cycle, even as new constraints come in, new design methodologies come in, new manufacturing techniques come in. We have continued to reduce their design cycle using our constraint-driven flow. With Sigrity added technology in there, you are sure that your product's going to work right first time because you've done power-aware signal and power integrity analysis.
All right, Hemant, that really underscores that this isn't experimental or just in PowerPoint. It shows that people are actually using this and it works.
Yes. That's absolutely correct, Amelia. We've had customers that have come back to us and give us feedback on what benefits they have derived. And this changes, as I said, the constraints change over a period of time, and we have customers use our constraint-driven flow with new constraints and still come back and give us feedback that they were able to reduce their design cycle rather than get it increased because of new constraints and new challenges in the design process. So here are some of the comments that I'm sharing with you, but this is an ongoing process with customers using it and giving us feedback.
So, Hemant, one thing I'm curious about, several months ago, you and I chatted about some new timing closure features. Now, tell me more about that.
You're right, Amelia. We have integrated the timing closure capabilities we talked about last time into the constraint-driven flow. In fact, the two work hand in hand. And what we have is a timing vision environment, Allegro timing vision environment. It's an innovative technology with smart target technology. And the feedback we've gotten from customers is that it accelerates timing closure by up to 4 times over traditional EDA tools and methodologies. Even with having a constraint manager that gives you the feedback, it is even better with timing vision environment.
Wow, okay.
So since we talked about it a while back, let me briefly tell you about Allegro timing vision environment. There are 3 elements in it.
Okay.
One is there's an embedded timing engine. So Constraint Manager gives you the accurate status of your design as you're writing your critical signals.
Okay.
It also gives you how much more you have to do to your signals to meet timing. What it doesn't give you is strategies on which signals to elongate, which signals to shorten.
Right.
So that's one of the things that we provide is a ability to help designers develop that strategy through real-time feedback on the canvas.
Okay.
Once the feedback is provided, once the strategy is determined by the designer based on the feedback on the canvas, we also provide utilities like auto-interactive delay tune, which allows the designer to pick a set of signals and let the system tune it based on the constraints in the constraint manager.
Gotcha. Okay.
So now the designer is in control of which strategies to deploy, when to deploy it, but he has the automated tools to deploy and get the job done fast.
Right.
Now let me show you a quick example of how that would work. In this particular slide, we're showing that there's a DDR3 or DDR4 interface going from a CPU to the DIMMs. You can select those signals and get into Allegro timing vision environment, and the display would then show you signals in red, green, or yellow. Red being too short a signal, green meaning meeting timing constraints, and yellow means too long a signal that you've got to shorten it. Once you do that, then in this particular situation, a designer may choose to meet timing for signals that are the innermost set of signals or the byte lane that's on the inside.
Okay.
And then once you select it, then auto-interactive delay tune can just tune those signals. So that gives the designer the control of which direction to apply this automated tools into. And that's why we call it an auto-interactive technology. But this is done within minutes rather than hours.
Yeah. So if anyone wants to check out more information about Allegro's timing vision, you can click the link and check out a previous Chalk Talk. So, Hemant, this sounds great in PowerPoint, but I know customers have been using this for a while, right?
That's right. And we have feedback from customers. In this particular example, Pegatron shared their savings using just the auto-interactive delay tuning capability and saved 68% of time to tune those DDR3 HDMI, USB 3.0, and SAS signals on a server board and on a tablet board. So two different designs, same set of interfaces, but we're able to do it in 1/3 the time, just using one utility.
Wow. Okay.
Now, we also have another customer that recently published their savings. It's Cavium. They used this Allegro timing vision environment as well as auto-interactive delay tune and auto-interactive phase tuning on their evaluation board. And this evaluation board had 4 DDR3 channels. It also had PCI Express and several other interfaces that are available from the CN78XX chip.
Okay.
Now, their challenges were impedance matching requirements, static and dynamic phase matching constraints, and a whole bunch of high-speed SerDes escaping from the east and west side of this processor.
Okay.
What they reported was they could tune the 4 DDR3 channels in less than 4 days using Allegro timing vision environment. That would have taken them 4 weeks to do.
Wow.
It's a very congested board with lots of interfaces, lots of high-speed signals, and would have taken them 4 weeks, and they did it in 4 days. And the good thing is the designer didn't have to go between the canvas and the constraint manager to figure out what to do next.
Nice.
It was all on the canvas.
Okay, so a lot of constraint-driven flow is based on nets that have constraints, but what about decoupling capacitors? Everybody has to deal with those.
Yes, everybody has lots of decoupling capacitors, especially if you're dealing with large pin count device like a CPU processor or large ASIC. So this is an area where very little work has been done in EDA industry. And what we've done is come out with the industry's first complete constraint-driven power integrity design process to help our users manage cost by reducing the decoupling capacitors that are not required, improve product reliability, but making sure that the decoupling capacitors are close to where they need to be, decoupling the right set of power planes, and optimize the product size. If you're using less number of components, you may not need as much real estate to put those components.
Right.
This is where we've combined the Allegro and Sigrity technology to provide an improved constraint-driven flow that is not available anywhere else. So let me share a little bit more about how that works.
Yeah.
So the constraint-driven power integrity design for PCB and IC packages, in that case, what would happen is design engineer would associate decoupling capacitors with components. And design engineer can do the planning of how many decoupling capacitors are required early in the design cycle, associate those decoupling capacitors with components, and provide that association through constraint templates to advise the layout designer on where those capacitors need to be placed.
Okay.
So now the layout designer has a guidance at the beginning of the design cycle rather than waiting till analysis is done after the placement is done.
Right.
So that's an improvement. So this is where constraint-driven flow, doing it right the first time, helps. And then what we've done is combine the IR drop analysis capability with the layout capability side by side, so the layout designer can look at the results of IR drop analysis, look at the hotspots, and move decoupling capacitors and figure out if that's going to help or not. So that combination of the two technologies from Sigrity and Allegro helps the layout designer get to the right power delivery network design capability inside their product.
Okay, Hemant, that's cool for power integrity, but what about signal integrity?
I'm glad you brought up signal integrity. So Sigrity has been known for power-aware signal integrity and power integrity analysis. For the signal integrity side of things, when you're dealing with these high-speed signals, you've got to make sure that you're accounting for the signal's path inside the package and on the die. Right. Especially on the redistribution layer. So what we provide is a way for you to plug the different elements of the signal that comes from the die, that comes from the package, and the signal on the board all together to analyze what we call the multi-fabric plug-and-play system-level power-aware signal integrity analysis.
Okay.
We make it very easy for engineers to plug those pieces together. We do the extraction, we do the connection, and we do the simulation for the user very easy to make sure that users are Sigrity sure. To make sure that they got power-aware SI analysis done instead of just an ideal ground plane analysis done.
Right. Okay, and in the beginning, we said we were going to talk about how Cadence's package design capabilities are going to fit into this picture. So, Hemant, let's dive into that for a bit.
Great. So what we provide is Orbit.io for die and package planning. And Orbit.io works, it's a planning tool that allows you to do ball-out planning for the silicon or pin-out planning for the package.
Okay.
And it ties into Cadence's IC design tools, Encounter and Virtuoso, as well as our system and package design tool. So it's the bridge between these tools to do efficient die planning or die bump-out planning or package pin planning. And the integration is provided through Orbit.io to all these tools.
All right, Hemant, this is great for people designing the package, but what if I'm not designing the package and I still want a more efficient board?
That's right. A lot of our customers do not design the package and chip. So a large majority of the customers out there don't. They just use the components that are available to them.
Right.
But there are many companies out there that want to provide an early feedback to their suppliers. They have the influence before a new part comes out, and they want to be able to provide the input to their suppliers based on the way they're planning to do placement. So what we provide is a way to take your route planning on Allegro, feed that into Orbit.io, and Orbit.io will then provide you with a pinout for the package that's more optimal for the board, and you can send that to your supplier.
Ah, okay.
So that way you are influencing what your supplier will provide you in future with the optimal pinouts. So that will reduce the number of layers that you have on the board and make your routing easier. If not number of layers, you make the routing much more easier, much faster.
So far, we've talked about board design, SI, PI, but Hemant, last time I checked, they don't sell boards down at Best Buy. So what about the enclosure part of this?
That's right. So the enclosure part is important. As you know, nobody sells board by themselves.
Right.
So what we've done is chosen to implement a new standard called EDMD. Schema. EDMD stands for Electronic Design Mechanical Design. Most people in the industry refer to as IDX. IDX happens to be the file extension, and the latest version of that standard is 3.0. So although I call it new, it's been out for several years, and it's supported by Cadence, Mentor, Altium, and on the mechanical side, supported by PTC, Siemens, and Dassault. So all the major ECAD vendors and MCAD vendors support it. So you would ask how we call it the most advanced ECAD-MCAD co-design, and the reason is because we implement the whole standard in its entirety. So we support the maximum amount of capability in that standard. For example, the standard supports accurate copper transfer. Copper transfer is important when you're dealing with shields on the board. So if you change the traces that connect with the shields, if you move the traces on the board, you want to make sure the mechanical designer knows the shield needs to map it. So shield dimensions can change, the shape can change.
Sure.
Also, even though we use this new standard, which is efficient because it's collaborative and it provides incremental co-design, we still want to make sure that the PCB designer doesn't do unnecessary iteration with the mechanical designer.
Right.
So what we provide is a native 3D viewing of the Allegro PCB design inside of Allegro PCB Editor.
Okay.
Customers can use step models to model their actual components.
Nice.
So they can get that like a connector model from the connector supplier, or if they have a 3D design tool, mechanical team that does the 3D component design, they can use that component inside of Allegro. And now they get an accurate view of the PCB, and they can also import the enclosure and look at the printed circuit board and enclosure together.
Nice, yeah.
So visually they can see if they have placed a component that's not going to fit in. So that's one way, easy way to avoid an iteration.
Right.
You know you place a component that's going to hit the ceiling someplace else, right?
Yeah.
So you avoid that kind of iteration.
Okay, Hemant. Now, I know you've had this situation, and I know I have. We've all had a situation where we've designed with a part, and then later, look at that, oh, it's obsolete or non-compliant or had some other kind of problem that made us had to redesign the whole board.
Right. You don't want to find that out
No.
after you ship the board. Or even before you ship the board, you send it to manufacturing and find out you used a part that isn't going to work for whatever reason.
Right.
Could be it's not RoHS compliant, could be it's too expensive, or could be, it's going to go obsolete in 3 months. You don't want to redesign your product for 3 months.
Right.
So what we do is when the design engineer is choosing the parts, when he's creating the schematic,
Yeah.
we tie into the corporate data systems and provide the different attributes that are necessary to choose the right part that will function correctly electrically, but also is cheap, has the right supplier, approved supplier, has the standards compliance, could be RoHS, could be anything else, or it's not going to go obsolete in the next couple of years.
Right.
So you want to make sure you choose a part. So right at the onset, the design engineer has the visibility to those attributes to choose the right parts. And that's how we tie the corporate data systems in there. And then we also, as the design is going to lay out, we also do validation of selected parts against business criteria. So there's a way for engineers or engineering managers to make sure that no parts are being used that are not part of a preferred part list or approved manufacturer list.
Gotcha.
So there's a way to check that. And then the other dimension to this is that we provide integration into PLM systems. So a lot of customers want to have structured design methodology.
Yeah.
And they use a PLM system out there, and they want to make sure that their engineers use the PLM system or use the PLM system for version control. Now, a lot of engineers don't like to get out of their own ECAD tools to interface with the PLM system because that's just a new tool they want to learn. They have to learn. And what they would like is really to get that benefit without having to learn a new tool.
Sure.
So what we've done is taken the Cadence's team design capability that shows the engineers, their team members, and how they're working on different blocks, different parts of the schematics. And we provide the version numbers of the different blocks or pages that engineers are working on. And we do the check-in, check-out of those different elements from the engineer's desktop and put that into PTC Windchill.
Ah, okay.
So now PTC Windchill is working behind the scenes under the hood, so to speak, and the engineers don't necessarily have to interface with the PTC Windchill, yet they're getting the benefit of what PTC Windchill provides. Now, this also means that those people in the company that want to look at the project architecture or different elements of the design, they can go to PTC Windchill and look at it. They don't have to be an engineer or use the engineering design tools to look at it.
Right.
So there's the best of both worlds for non-authors, non-implementers, as well as make it easier for design engineers to be able to interface with PTC Windchill.
Okay, so Hemant, now we're working with corporate data systems, parts from multiple partners, but most of us don't make our own boards. So we have to hand a pile of data off to manufacturing, which can be at times a bit of a nightmare.
It is a challenge, and most companies deal with myriad of files. They provide Gerber files, provide ANSI drill files, they provide test files, they provide netlist file, and all these are different file formats, and they all need to be in sync when they're produced, or you get a board that is built that's not going to work.
Right.
And a large majority of the companies out there, 95+% people, deal with this challenge. So in the industry, there's been an effort on trying to make the handoff to manufacturing more efficient. There's a standard called IPC 2581. It's been out there since 2004, but until recently, nobody was using it. So in 2011, a group of companies, about 12 companies, created a consortium of PCB design and supply chain companies. And the idea was to make sure that the standard is interpreted correctly, the EDA tools produce it, manufacturing companies consume it, and that the interpretation on all sides is accurate. So the consortium was formed in the middle of 2011, and now it's grown to 65, 66 companies.
Wow.
And a lot of major companies like Cisco, EMC, Ericsson, Qualcomm, Fujitsu, NVIDIA, and there's a whole bunch of them on the website. You can go to ipc2581.com and look at the members there. And it's growing. Every week we're adding 1 or 2 new customers. And the idea was to ensure that 2581 gets adopted. And we've come a very long ways from software producing it to validating it to enhancing the standard collaboratively in an open environment. It's an open, neutral, global standard. And that's the important thing. It's one file instead of myriad of files.
Yeah.
And it's a modern data format. And a lot of companies in the industry are going this way.
Okay, so you've streamlined the handoff, but what about stack-up designs for designs that have stuff like DDR4, PCI Express, the special stuff? What about that? Now, I hear some people use email, spreadsheets, and the occasional carrier pigeon.
You're right, Amelia. There's a lot of things that go on with the fabricator early on before the layout even begins.
Right.
Companies that use these standards you mentioned send their impedance requirements to their fabricators. Fabricators then send emails, Excel, spreadsheets, PowerPoints, PDFs, and those are then interpreted by somebody on the system house side that then interprets it and puts it into Allegro, PCB Editor, or their ECAD tool of choice, and then do the layout and then hand off that layout to the manufacturing And this manual entry after the fabricator gives you what they can build according to your requirements is error-prone and time-consuming.
Yeah.
And if you have multiple iterations, it can be very frustrating because you're manually re-entering a lot of things.
Sure.
Or a lot of companies, some of the companies, not a lot of companies, have the wherewithal to write some tools of their own to automate that process. But every company's got to do that. This is really a very simple thing that EDA industry should be able to solve now in this 21st century, right?
Totally.
So what the consortium has done is enhance the 2581 standard to extend the stack-up definition so that this collaboration is possible electronically.
Okay.
So the process will still be the same. You as a system house pass your impedance requirements to the fabrication house. Fabrication house can then send you the IPC 2581 file, stack up in that format, that can then be consumed in a tool like Allegro PCB Editor directly without any manual intervention. So now you know, if you agree with that stack up, you know that you're building a board on an approved stack up.
Right.
If you want to tweak it, you can tweak it in Allegro and then make that change and send the 2581 file back to your fabricator. Now you're dealing with electronic exchange. This is something that should have happened a decade or two ago. But with 2581, companies out there can use this electronic stack-up exchange with an open, neutral standard.
Excellent. So, Hemant, let's wrap up this bad boy.
All right. So, Amelia, so we talked about product creation involves more than just the PCB design, more than how efficient you can be with schematic creation, more than how efficient you can be in interactive editing on a board.
Right.
It is about making sure that the board is designed with support from power-aware SI and PI analysis tools, which is tightly integrated so that you can design it correctly fast. We talked about power integrity, that's the constraint-driven power integrity, that's industry's first, that we've integrated Sigrity's technology for power delivery network design into Allegro flow. So now customers can have a constraint-driven power integrity flow. We also talked about Allegro timing vision and added data points we got on how companies like Cavium and Pegatron were able to tune their signals 4 times faster than traditional methods. So not only we have a best constraint-driven flow, but continue to enhance it to make it even faster for our customers to design their boards that will function correctly the first time. We have the best ECAD-MCAD code design solution for fast, accuracy, PCB, and enclosure design. And we've integrated our design tools with the corporate data systems to ensure that you don't have unnecessary respins of the boards with parts that may be obsolete or parts that are not compliant.
Right. Well, I think that's all I have time for today. Thank you so much for joining me, Hemant. It's always a pleasure to speak with you.
Same here, Amelia.
Before we go, don't forget to click that link. There you can download a tech packet that includes an article, white paper, and customer success stories about this topic. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.